Take it away.
Thank you. Okay, so when I started putting this together, at first I was thinking about lots of geochemistry, and then I realized that a lot of it has already been covered. So I actually am going to focus more on some of the plate and plume motion kind of components, and we'll get to some geochemistry and how I've been using it, at least, towards the end of it. So not a whole lot of XY plots, as Matt sort of explained to me I shouldn't have too many of. So in all fairness, several people have been working on the stuff that I'll be presenting at the end. So they are down here, Matt and Anthony primarily, and then two of our students have been working on some of the things that I'll show a few parts of later. Okay, so there's sort of two things that at least I'm interested in looking at when you go through these exercises of looking at what these plumes might be doing. You can do sort of the more traditional thing, which is basically look at how are plates moving over the mantle and assume you have somewhat of an absolute reference frame from these plumes so that you can sort of tell how these plates are moving. And then the other thing you can do is, if you have some idea of how these things actually are behaving over time, then, of course, then you get back to the Holy Grail. Where are all these geochemical reservoirs hiding out in the mantle? Where are the conduits anchored? And so this is, of course, the part that we're after in the end. I'm going to spend more time on the first part. This is more of a long-term thing, and I'm not sure we'll get to talking about that today. That depends on how much time I have left. All right, so I'm going to break this up in three parts. First, I'll just sort of talk a little bit about plate motion models and the sort of traditional idea of having fixed plumes and how you set up a absolute plate motion model based on that. And then we'll move on to the fact that plumes probably aren't fixed. Review a few reasons why that might be, and how we can still, well, I'll argue you can still use them to get some idea of how the plates are moving. We'll get to why that is later. And then in the end, I'll talk a little bit more about the geochemistry and how we do need geochemistry to actually be able to track some of these hotspot tracks that are sort of this reflection of what plumes might be doing. And hopefully we'll get to this part where we are now, or at least we as in the people on the first slide of this presentation. Okay, first part. If you squint, you might see lots of red dots. So people do exercises of figuring out how many submarine volcanoes might be in the oceans. It depends on your scale. What I did is I cut it off at about 500 meters, which is the traditional seamount cutoff. And then at that scale, there is tens of thousands of volcanoes on the seafloor. And then Anthony has nicely highlighted in this map that I made where there are a few chains of things. So you might notice there's other chains of dots that are probably not necessarily related to hotspots, but are running around fracture zones and things. So lots of chains. Some of these may be hotspots generated by plumes. Some of these things may be something entirely different, either related to plate boundaries, or we get lots of isolated volcanoes too that are just sitting out in the middle of the Pacific. So these kinds of things are the things we'll start talking about. You're mostly familiar probably with Hawaii, and for us hotspot aficionados in the Pacific, Louisville is the other big one, because these are the two really long trains of volcanoes. All right, so following up a little bit on telling the difference between different things. So people have, these are just a few pictures of this, but different people have spent time trying to figure out which one of these chains might represent what kind of process, whether it is a nice deep plume or whether it's something right near the plate, or whether it's something off of the top of, well, they're not super plumes anymore, but whatever that is, right? So this was I like this because it came up with a couple of different reasons to have different things. And if you look in any type of new plume catalog, usually you'll end up with a variety of different things that have to be either shallow or deep. the bottom line ends up being that out of the, say, 40 or so plumes that usually show up, probably 2/3 tend to be thought of as coming from somewhere deeper down. So that being the case, if there are plenty of deep-derived plumes, we should be able to keep marching on and sort of go with the old model of making hotspots, hotspot tracks that give us an idea of how the plate moved. Bottom line, we have plenty that are deep. So I figure you probably have seen this before. So this is the traditional plot of distance from, in this case, Kilauea versus age in Hawaii. And so this gets older as you get further away from the hotspot. It's age progressive. You can do the same sort of thing for other hotspots. So this is an example for Samoa. The reason I put this up is this little bit here. These volcanoes take a while to build. If you're going to go from the seafloor up to the surface, in the case of Hawaii, you go up to 4 kilometers, so you stretch 9 kilometers. It takes on the order of 5 million years before these things are really done. So when you go through the exercise of trying to relate the age of the volcano with where it is on the plate, what that might mean for the hotspot track, this is immediately one of our errors, right? I go pick up a sample, particularly if it's a seamount. I don't know where in that 5 million year time frame that sample was. It probably is towards the tail end, because most of what we do is dredging. But if you get a rock from the bottom of the hill, it could be an older one. So we never really know exactly where in the volcano we are, unless it's like a Hawaiian volcano. But that's where the islands are in Hawaii. The rest of them are seamounts. Same in Samoa. You have about 5 million years of island. After that, everything else is underwater. So there is an age error in there.
Jasper, I'm a little bit confused about the plot in the upper left and what you're saying then.
Okay.
If you got rid of that sloping line,
yeah,
it's not obvious there's a relationship at all, right? So are you saying that we should actually always look at the upper?
Yeah, so the idea is, ideally speaking, the only thing that you would want to do is think of, if you have a plate moving over a fixed object, I'll get to moving plumes in a little while, but if you assume they're fixed, the best thing to track would be the first occurrence of the volcano. That's a problem because that's the middle of the volcano, right? So we're never going to actually know exactly when that was. So you go by the oldest one you have. And that's the best we can do. And so every one of these is going to have a sampling bias effectively on that number. So even though each one of these dots can be at this point measured to within a fraction of a million years, particularly for the young ones, that doesn't really mean much compared to the geologic error or sampling error. Yeah.
So this 5 million years. This is 5 million years. You actually, when you talk about the Big Island of Hawaii, I thought the building time for Big Island Hawaii is about 1 million years.
Yeah. So I didn't put the slide in to discuss the full history of these things, but usually you have multiple phases to build these volcanoes. The big shield builds in about 1 million years, but then activity tapers off for a while, and then a number of these, not all of them, but a number of them pick back up in a rejuvenated stage.
That's right. Like
after like 1 million years later, and that can run another year or two or so million years. Okay. So the total stretch is 5 million. And particularly when you're fishing off a boat, you don't know whether you got that last bit. That's the bottom line. Okay, so that's one thing to keep in mind when we're doing these exercises. There is some play in the age, and given plate motion, which is going to be on the order of tens of kilometers to, say, 100 kilometers per million years, if I'm off by a few million years, I can be off by a few hundred kilometers in where this thing came from. All right. So how do people make these plate motion models? They used to just go by each chain and then find a pole that worked for all chains. The Wessel folks at this point, what they do is they basically pick the beginning point, is find the hotspot for all the chains. You draw a polygon between them, And if the hotspots are fixed in time, all you're doing is rotating the plate. It's like a rotation on a sphere. So the polygon has to stay the same. The hotspots aren't moving, so the polygon can't change. And so they literally use a geometric method to just move that polygon along the change that they have identified in the Pacific. You can do exactly the same thing in the other ocean basins, right? So this is the exercise. Find the rotation, the Euler pole that actually rotates so that you can maintain your polygon. Now, I started that out with, so you just start out at the beginning of the hotspot. So tell me where the hotspot is, please. We don't know where the plume is, right? So you could go with, well, here's the newest volcano. Good enough. Or you can go with some seismic model or some other geophysical observable and say, okay, well, I think this is roughly where it is. If I go with this, I have a good bit of error in my estimate. If I go with this, well, that might be right. But who knows? So what Paul Wessel does is he's taken his, this is back from the late 90s, but he still uses this. This is what he calls hotspotting. So basically what he does is he iterates. He assumes he knows where the hotspots are, does the polygon exercise, but then there's a misfit. So then he basically goes back and he adjusts the original starting locations and tries again. And the way he does that is by coming up with a model and then using that model in reverse. So you see these lines running here. This is what he calls the mantle flow paths of how this moves. And so if you take each volcano and track its mantle flow path back, which is basically ends up just being the plate motion model in reverse, you end up with these little crosses. And so where the intensity is the highest, the density is the highest, is where he then sort of iterates to the highest clustering. I personally, I'm not sure the mantle flow paths really give you much, because in chains where you don't have this bend, means you just get straight lines only, and there's no crossing, so it doesn't really help. But what this does effectively is it basically fits the model, and then effectively just looks at where the individual volcanoes end up reconstructing for Hawaii, for any of the other hotspots, and says, how close are these reconstructed locations where these volcanoes came from? If that's a really nice tight cluster for each one of these hotspots, I've probably iterated to the best plate motion model. So this is his way of doing that. I would probably just look at the clustering, but anyway.
Jasper, if there is a bend in the chain, that means there was a change. One explanation is that there was a change in the direction of plate motion. So how can you do that?
How can I
cross the bend?
Well, that's what this technique actually has to rely on, is that there is a bend. Otherwise,
so
these
you already
tracks
know
don't
the plate
cross again.
So you already know the plate motion.
Well, so he follows with the geometry, with the previous step. Oh, this one. You just set up the problem as, I think I know where the start of these things is. So I pick Loihi, I pick the Easter Island, Louisville is a really big problem because we don't really know where that is. You just pick locations and you try and come up with your first iteration, your first model, and then that has to have a bend just to follow the Hawaiian Emperor bend and the Louisville sort of curve. And then you have to go back and adjust it to see whether you basically can get the reconstructed locations moving each one of these volcanoes back to its original location so that it tightens up as well as you can. Then you found the best model. That's effectively what we're doing. Or not we. I haven't done this, but... Okay, so the next step, what do you actually have for data? So this is what Paul uses as his database. So they have a number of chains identified, and those are the geometric constraints to do this exercise. So you can sort of see here there's a little red star for each hotspot. This is time 0. This is time 0 for Hawaii. And basically, what you're going to do is you're going to start following that polygon along all these different parallel tracks and find the rotation pole that allows you to just make that one simple rotation. Now, it should be fairly obvious that you have 2 long chains and lots of smaller ones, right? So, back to about 80 million years, both Louisville and Hawaii Emperor give us a pretty strong constraint. Another way to say that is both of those chains are dominating the first 80 million years because they are pretty much continuous all the way through. And then there's a whole bunch of these shorter chains that contribute to the shorter time frames. Most of these are about 20 to 30 million years, roughly. And then there's some of these older ones here, back in the Western Pacific as well. So that's sort of your data set. There's one thing that I put here to point out for later. If you look at these rotations, basically each rotation means that the further away from the pole you get, the more the distance starts changing, right? If you're close to the pole, you're only moving a little bit. If you're further away from the pole, you're moving a larger distance. This matters when you start looking at the angle. This is called the opening angle in the model versus ages. So what we've done so far is we've just basically set up the rotations, right? So going through this exercise, now you know how to move the plate along this geometry, but there's actually no time component in here yet. So now you have to add a time component. So here are the model angles for all these dots. And so this is basically putting in, here's all the different colors. These are all the different hotspots that you just saw on the previous page. And they go back in time. And you basically start associating ages with these dots. So the exercise then becomes to fit some sort of relationship through these dots that describes how the rotations change back into time. And that then gives you your plate motion model. Now, there's one issue here. You see a number of these isolated dots that are far off, and there's a couple of groups even that are relatively far from this trend. And so the reason that's an issue is that this is a purely geometric technique. And so you're basically just saying, okay, if I see parallel trends, I'm going to just fit this polygon and make it go back in time and fit that trend. That means, in particular for the group I pointed out on the previous slide, is this corner here. What does that corner look like? Is there anything in any other place in the Pacific that reminds you, or that this reminds you of? Anybody heard? What's that? Yeah, okay. So, does this look like a bend to anybody? Sort of the beginning of a bend, right? And so, what Paul does is he assumes this is the same as the Hawaii Emperor bend, and then uses this in his technique, in his geometry. The problem is that that didn't go right. The problem is that the ages don't match. So you're basically adding the ages after the fact, so you're ignoring the fact that you actually know this isn't working. Okay, so that's the first issue with the exercise. There's other things that you can do to sort of prove to yourself that this works. Oh, yes?
Jasper, can you go back one slide? So with the green dots, I see other bends.
You see other bends, yes?
Right. If you look at the age of those bends, do they coincide better with the bend in the Hawaiian chain?
Do you have any in particular that you like? Basically, this is the kind of bend that you have to sort of look at. If you want to do Hawaiian Emperor, this bend corresponds to this bend.
Yeah.
This actually turns out there's another bend over here, and I'll get to that one later. That actually does correspond to the Hawaii Emperor bend. They just did the ages wrong here. These shapes here are different because they are further back in time. We'll get to those in a little bit too, because those are fun too. There's some assumptions in where those fit in. Okay, so the second issue with this. We'd like to show ourselves that we know that this is right. So what you can do is you can say, all right, if all the plumes are fixed in a mantle and the plates are just moving over the top, I should be able to just go to the other ocean basins, the Indian or the Atlantic, and look at plate motion, record it there in a hotspot, and then hop my way across a plate circuit and translate how the Pacific plate would be moving across that hotspot reference frame. Or another way to say it is, I can basically take what track the Atlantic hotspots predict and plot that on the Pacific map to show what the Atlantic hotspot thinks, or what the hotspots think the Hawaii Emperor chain should look like. So if that's right, then I should be able to predict quite nicely what that looks like. And so we've actually known since the 90s that actually doesn't work. So you go back from 0 to about 30 million years. It works pretty well. These ellipses are the rough error estimates in the plate motion model. I think those are actually fairly conservative error estimates. This is mostly from the rotations. I don't think they necessarily added in errors from the plate circuit as well. But anyway, so back to 30 million years, this works pretty well. And then after that, it really doesn't work very well, right? This is 67 million years. That should be over here somewhere. So you're missing out on the bend, more or less. So this has bothered plenty of people for a while now. So we can't predict the Hawaiian Emperor bend simply by assuming fixed hotspots. The other thing is, and this is something people have worried about for a while, this is an old map, right? This is from 1995, so it's about 43 million years at the bend there. If you have such a dramatic change in the plate motion, or in the orientation of the hotspot, that implies you have to have a very significant change in plate motion. That can only be true if there really something significant changes in the plate tectonics of the area. So you would expect to see something on a larger scale shifting, maybe a new subduction zone or something relatively significant changing. And that doesn't happen until about 50 million years. And so people have spent some time going back there. I didn't put the slide in, but they've gone back here, sampled it a lot more, and dated it. And it's dated around 48 million years now. And with a lot of, well, not a lot, but with some hand waving, you can make it look like 50 million if you want. So age-wise, it's probably okay, but this still doesn't work.
Sorry, does that have to coincide exactly in time, or can there be a lag?
There could be a lag, but this is earlier. Or no, you're right. This is later, but I don't know whether it's 50 versus 43. That's 7 million year difference. I mean, at some point, if subduction zone starts pulling the plate in a totally different direction, that should start getting recorded. I mean, yeah, you have your errors in time based on when the volcanoes show up. Right, you have that 5 million year time frame for building these volcanoes, but I think most people were not too happy with this.
Tell you something about viscosity in the mantle, right?
Yes, sure.
Jasper, but isn't this the issue that came up earlier, that you should always look at the youngest age you find at any location?
The oldest.
Oldest.
Right, the top of the block. That's probably what happened here, right? This is 43 million years, and they went back and found a rock that was about 48 million years. All right. Something even worse for fixed hotspots. I showed you a plot where you have opening angles against ages, and Paul Wessel made this nice model back in time. If you look at that in detail for the first 15, 20 million years, Samoa, and then we have there's a couple of different chains. Foundations are in here. Hawaii is down here somewhere. There's a whole bunch of different chains. They all have slightly different angles. If my hotspot is fixed, this is using the opening angle, so I'm just rotating. It doesn't matter where I am on the plate. The opening angle should always be the same. If this model is just modeling having a fixed plume over a moving plate. Instead, I find different angles here, different slopes. That means these things are not moving according to a fixed hotspot reference frame. They should all be on top of each other. Of course, there is the time component, the ages. So maybe for this blue suite here, we managed to somehow sample sort of systematically too young every time. Seems unlikely. So there might be something else here that's telling us that you either need moving plumes or your plates aren't rigid. I prefer the moving plumes. It's easier to deal with. All right. So we've moved our way through building an absolute plate motion model based on having fixed plumes. So now we'll move along into moving plumes. So first, gratuitous plume figure. I only put this in because it has a moving plume, not much else. The idea is there's options why a plume might not be just sitting at the bottom of the plate, coming vertically up and just sitting there. And so that's what's going to affect what you see at the surface. If this thing is moving, the standard model of build a volcano over time in a nice straight line is going to become messy. If this plume is moving back and forth in the direction of plate motion, your H progression is going to go and fall apart. If it's moving across track while your plate's moving this way, then your plate will be recording plate motion plus some sort of wandering plume. So you'll be trying to fit a plate motion model to islands that went left and right compared to where the actual plate track should be. All right, so Arduino in, 2009, reviewed a number of different ways you could think of why plumes might be moving, including things like, well, if you're close enough to a ridge, maybe it just gets channeled towards the ridge. You could look at, they're basically trying to show that if you have very strong flow in the upper mantle, you may be able to deflect things around. You can have large-scale convection moving plumes around. I forget what this was. Oh, yes. If you have plumes essentially migrating through the mantle to sort of gather in the middle, that would end up moving the plume around. And then this is kind of similar, I think, to the first one. It's this idea that if you're stuck sort of being funneled towards a ridge, if the ridge system is actually moving away from the plume, eventually the plume may sort of snap back from being focused towards the ridge to, once that distance is big enough, sort of flopping over back to where it actually wants to be. And he even suggests that there's a distance for this on the order of 1,000 to 1,500 kilometers. I forget where that came from, but what's that? I don't know. Yeah. Well, the idea is that they're being pulled in this way with I guess with corner flow, but I'm not even sure what the idea was anymore. And then eventually, once this distance is big enough, they're not being pulled in anymore, so they kind of meander back to where they want to be. No, this is where they're being pulled in. This is where they just get to go where they want to go. No, just because of buoyancy, they want to go up. They're being pulled in here for a while, but then at some point when they're too far away to be pulled there, then buoyancy just makes them go up again. And then there's some time frame in between where they do something funny.
You can kind of think of them like a blowtorch, like going through the plate, right? And it's easier for them to follow the path of lesser viscosity and resistance towards the Minnesota ridge where there's hotter stuff. But then once it's far enough away, they just go back to blowtorching through the plate straight up.
Yeah, something like that. Yeah. Okay, so lots of ideas why this might be the case, why things might be moving. So the next thing you should be asking is, well, that's nice. Is there proof that this might be working this way? And so this was the sole idea for a while in terms of going out there and trying something. So if you go to the older stage of the Hawaiian Emperor chain, we know that right around the bend is when things get really weird, because according to the Indo-Atlantic hotspots, the plate motion should be pretty much marching on, while in Hawaii it heads north. So these folks went and drilled a number of the Emperor chain seamounts, and basically did paleomagnetism, trying to figure out what the paleolatitude was at which these seamounts were erupted. So along the Hawaiian chain up to the bend, the paleolatitude only shifts by, I think it's up to a few degrees at most. If not, it's like 2 degrees maybe. I forget exactly what it is. But then once you go past the corner, these things seem to suggest that the latitude at which the hotspot was erupting increases by almost 15 degrees over on the order of maybe 25 million years. Now, the error is large on these things, so if this is true, here's the plume motion you would need to sort of make the model fit with sort of a fixed plume model. So up from 60 down to 30 millimeters per year. So that's basically double in variation. And this assumes a few things. You have to assume that you're sort of averaging enough that if there is any kind of true polar wonder or anything along those lines, that evens out. I'm not sure that's true. The other problem is you're drilling a seamount. And I don't have time to go into this too much, but you may be aware that these large oceanic volcanoes tend to fail and make big landslides underwater. And so when you drill into one of these things that has a coral cap on top, you're not necessarily sure that everything you're drilling through is truly still in its original position. It may have moved. So there are some issues with this, but this is what it seems to suggest, is that paleolatitudes changed. And so if that's the case, the hotspot was sitting further north and moved south while you're in that Emperor stage time frame. And then once it got to around the bend somewhere, it sort of slowed down and sort of sat in the same place. All right, so if that's the case, this would give you an idea of an overall moving plume, at least for a little while. There's other things you can do. You can say, or there's another indication that there's something funny going on in Hawaii. If you go back to the northernmost Emperor seamounts, their chemistry, here's the strontium isotopes, geochemistry. Here's the strontium isotopes along a number of these volcanoes in the Emperor chain. As you go along them, and you get to the northernmost that sits right in the pretty much into the trench. It's about 80 million years. Its composition is pretty low in strontium. And so at this point, I should have just put this on the slide. Once you get down to that sort of level of 702-ish, you're down into this area here. All these blue circles are all morb-like compositions. So the Hawaiian chain, as you get close to the top end of the Emperors, basically looks like morb. And the reason for that, probably, this is a reconstruction from about 80 million years. Here's Hawaii, and here's the ridge system. So you're within about 7 degrees or so. You're within that 1,000 to 1,500 kilometers that Tarduno suggested would be the distance over which you might interact with the ridge system. So from chemistry point of view, it seems like that might actually be what's going on. And then maybe the motion you're seeing in the paleolatitudes is, if you let this go with time, the ridge system moves away and eventually this hotspot becomes free of the ridge again. All right, so we have some ways to come up with moving plumes, some reasons why they might move, some observations that they might be moving, like this one or the paleolatitude. So then the question is, does this actually help? Oh, we already looked at that one. So this is work from Steinberger from a number of years ago, a decade ago actually. So here again you're seeing, he decided to do gravity maps, that's why they're yellow. But you can still see the volcanic change. So this is Hawaii. Emperor, Louisville's over here, and then Tristan and Reunion are two hotspots in the Atlantic and the Indian Ocean, just so you can sort of see how well it fits in all the ocean basins. And so what this does is it shows you predictions, trying to have a reference frame with moving plumes and how well you can fit the hotspots in all the different ocean basins at the same time. So you have predicted paths based on different models. And then these colorful little worms with little dashes on there are basically how, actually where does it go here? It's this little thing here. They basically show you how the plume is moving over time in this model. The nice thing is that from blue to red, you're basically having the actual hotspot move in the same direction that paleolatitude description said it should be moving, right? So this actually, having that component of motion in there makes the fit a lot better, although it still doesn't fit in the very northern end, while, for instance, Louisville actually does seem to follow along the chain quite nicely. So there's still some problems. This doesn't seem to be perfect. All right, so I didn't tell you what he actually did to make this work, so let's do that. So what goes into these moving plumes, is you have this combination of a density structure from tomography, plate motions, and an assumed viscosity structure to drive a global mantle convection sort of pattern. And then you have two options. You can either nail the bottom of your plume into the core, and it sits there, it's not allowed to leave, but the rest of the conduit can move, and then you have to end up in the same place. Or you can have the bottom and the top basically freely float through the mantle. So in this case, it's not nailed down in the bottom, and it starts sort of sweeping along. Right? So we have two options basically in this kind of thing. And yeah, it's up to you whether you like one or the other, I guess. So these are sort of your options if you want to use this kind of approach. If you want to try and explain how these plumes are moving over time with one of the models that Tarduno described is this whole mantle sort of flow moving these plumes around. This is what Steinberger's version of that looks like. And as you saw, it does a reasonable job. It doesn't do a perfect job at explaining the tracks.
So Jasper, I'm wondering where the biggest weakness of this approach is, where the most improvement could be made. And I'm wondering if would it be the density from tomography?
Well, I think these are all your variables, right? If you don't like the density structure, you can change that. If you don't like, I think plate motion is probably pretty well understood. Viscosity and density, and then this option here, those are your big options. And I don't know how much different it's going to be. I mean, this is a global model, and in the end what happens is in these models, the main amount of motion comes from upwellings where the LLSVPs are effectively, and downwellings around them. So most large-scale models are going to produce a similar sort of structure probably. Torsten? Oh, sorry.
I thought the challenge in geodynamics was to fix plumes more than to make them move around.
Fix plumes rather than what?
Make them move around, because they generally move around, but they're more fixed than they seem to be in models.
Well, I haven't made the point yet, because I think that's one of the next few slides. But the bottom line is, if you compare velocities of plates versus how much these plumes are moving, it turns out that the plume motion is less significant usually than how much the plates are moving. So you still don't want them to move a lot.
Just to comment on that, the reason for that behavior is, again, that the lower mantle is presumably higher viscosity.
Yeah.
And so you have less of a motion of the plume conduit in the lower mantle compared to the upper mantle, and your assumptions about the viscosity structure will affect these conclusions.
Right.
And so I would like to note, right, and Jasper is perhaps going to show that, there was a recent Nature paper by the Earthbite people that improved on the fit on the Hawaiian plume, right? I don't think they discuss if they jointly improve on the fit on the other Pacific plumes. And that gives you some reflection of the differences in the modeling approaches. But I think more importantly, you have to realize that, you know, hotspot fixity in itself is not just sort of, you know, amusing. It's also often used to define an absolute plate motion reference frame. And that particular reference frame falls into the plate reconstructions. So they are, as such, not that well constrained, right? And the way to make progress is what Dubrovin did with Torsvik and Steinberger, and what the Earthbite people have been doing, is to ask the question, can we find plate tectonic reconstructions that are consistent with certain assumptions, including, for example, hotspot fixity.
Right.
And how do our reconstructions change, right? And those folks are working on that.
Right.
So it's important to realize that there's a feedback, and we'll never be able to get at any insights if we're just addressing one aspect of the problem.
Yep, no, that's true. I did not put the latest Nature Geoscience thing in. I put this one in just to sort of show you this is an evolving topic. People are working on this, and it does still change. And so these are just the worms sort of showing over their model runs how the motion changes in that particular iteration, but this is still ongoing.
So Jasper, if you go back 2 slides back where you were where you were comparing the Reunion and Tristan versus Hawaii, could you comment as you go from one plate to another? Some people have argued that there might be uncertainties in the plate circuit models, and how they sort of feed back as an additional source of uncertainty in these reconstructions and comparisons.
Yeah.
Yes, thank you.
You can choose how you do this. So, and this goes to what Torsten was saying too, is this is all intimately linked, because you have to go and start assuming you actually know exactly how the relative plate motion between these plates works through time. And if you use one solution versus the other, the fit changes. So that's the kind of, that was actually one of the points that they made in this paper, is that various ones of these lines are various ways of doing that reconstruction. And that obviously changes how this fits. Torsten, you had another comment?
Well, just to briefly follow up on that, I'm not sure if you have the figure from the Dubrovin paper.
I didn't put that.
Because they show that plate reconstructions on all oceanic basins work much better if you allow for the hotspot motion that is predicted by Bernhard Steinberger's models. However, once you reach 50 MA or something like that, there's a big discrepancy, and you cannot jointly explain Indian Ocean and Pacific Ocean hotspots, for example. And that might be because there's something breaking down in the convective scenario, because the models aren't good enough. But at some point, you run into a situation where something is inconsistent globally, even if you allow for moving hotspots.
But that's where it breaks down, actually, too, in the reconstructions. Walking your way from the Indo-Atlantic to the Pacific domain gets really hard when you get to the 50, 60 million years, because you run out of spreading ocean basins. And then it's really hard to...
Is it issues with the plate circuit, uncertainties in the plate circuit, or?
Well, this is what the Earthbite people are working on, right? They're iterating, and they're trying to jointly refine the plate motion models to do as good a job as possible to some assumptions.
Right.
And I have a comment that relates to what Matt's question initially, is that we can play in convection models with contrasts of viscosity or the conversion between tomography and density separately, but like Max showed in his talk, constraints on viscosity structure are coming from the conversion between velocity to density. So they're kind of tied together at some level.
Yeah. Okay. The only thing I'm trying to point out is that they are this modeling exercise is based on a number of assumptions, and it's up to you to decide whether you think they're all reasonable.
I actually make a comment. I think this effort to computing the possible plume migration in the mantle in the presence of the global circulation is useful effort. But I also would like to point out that there are a lot of dynamical difficulties with this kind of models. There are a lot of inconsistencies, and I mean to tell you the simplest one, okay, Sternberg's model cannot predict any toroidal field because it uses one-dimensional viscosity, and so that actually, if you think about the hotspot reference frame, right? And there is this degree 1 toroidal field, and that is this net rotation of this field relative to this whatever the mantle you have there. And because we know the angular momentum is conserved, so that which really means that below the lithosphere, the mantle actually will, as a whole, will have rotated in the opposite direction. And Sternberg kind of model can never do that, right? And Sternberg's kind of model, if you use this if you use actually plume, hotspot reference frame, and his model, the entire mantle will rotate the same way as the surface plane. And I think, and of course, also when you talk about the plumes actually they got generated for good reasons near the command boundary. They typically generate in these places we call the stagnation point. And so, and there are dynamics that will work out in its own way, so the plumes actually will form there, and that's a stagnation point. And I don't think you can figure out that by simply using the tomography models. There's just, there's a temperature-dependent viscosity, relatively complicated dynamics that tell you, well, somehow the plumes got to form there, got to generate there. And so I think that aspect is also very, very difficult. I mean, I guess that's all I'm saying is this effort is very useful, but we still have to be very, very careful. These models are extremely simple. There are internal inconsistencies there, and we have to be very careful about that.
Fair enough. Yes, Thorsten?
We're discussing it.
Okay. All right. Let us know. Okay. So I'll come back towards the end to one thing that we've been trying to do to sort of start comparing what they're doing with some of the geochemical and geologic evidence to see how well they're doing. So we'll get back to some of this a little bit later. Where was I? Oh yes, we got to this point. So that's the whole point here I was trying to make was this is still ongoing, and basically what this does for us, it gives us a prediction of how the plumes might be moving in this large-scale flow. And Shizi's point is really important in that sense. That really is what they're trying to do, is they're setting up a large-scale flow. They're not trying to actually model where the plumes are in this model. They're just computing a large-scale field and then displacing or figuring out how a conduit would displace in that. All right. So we can go back to thinking about how well this is working. From the paleo-latitude stuff I already showed you about Hawaii, and then a couple of years ago, Anthony and a number of other folks went out to drill Louisville and do the same exact exercise. Okay, if Hawaii is, before the Hawaii Emperor Bend, if Hawaii is drifting in terms of paleo-latitude, suggesting the plume might be moving, what's Louisville doing? So they don't have as nice of a figure in their paper, so I have to do it with a table, sorry. But the bottom line is the paleo-latitudes don't change much, right? So it goes from 40 to 50 in terms of these archives, and then their actual constraints are only a couple of degrees. I'm trying to figure out which one I was supposed to be looking at. This is more than 5 degrees. Yeah. No, I'm not sure anymore where that came from. Well, anyway, their argument is that it's within 5 degrees. I'm not sure whether this one was ignored or not. I can't remember. The bottom line that they argue is that within the Louisville chain, the suggested shift in paleo-latitude as you go past that Hawaii Emperor Bend point towards the trench is that the actual latitude of the erupted basalts only changes on the order of a couple of degrees, where in Hawaii it's 15 degrees. So it doesn't, if that's the case, it doesn't matter whether you believe what Steinberger does or whether you believe any of the models for plume motion that Tarduno puts up. If this kind of exercise is actually giving you an idea of how the latitude of eruption changes over time, Hawaii is changing much more so than Louisville is, which means these things are not moving in unison. One of them is moving rather fast, the other one is moving a lot slower, right? So that would suggest that they are not necessarily doing the same thing.
Jasper, to compare this to the Tarduno's plot where you had age versus latitude, paleolatitude, the error bars in the paleolatitude measurements
are big,
very large, and that's always been like the least convincing aspect of this story. And I'm wondering, why are the error bars so large? I'm not a paleomagician, so I can't really.
That's part of where I'm also not a paleomagician. So there's problems in some of those assumptions. Yeah, maybe Doug wants to say something here. I don't know. Instead of me waving my hands about this.
Well, one of the sources of noise is a secular variation. If you expect 20 degrees of scatter on any one flow and you want to sample, to average out that variation, you need to sample like independent samples every 3,000 years for 6 or 8 times, and it's not clear to do that in a drill hole.
Right.
Another thing about this specific issue is it's not proper to simply compare the paleolatitude because of spherical geometry. You might expect the polar wonder to have a different change in paleolatitude at a different location. So that's an incomplete test, just looking at that.
Right.
The discrete samples should be more reliable than the archive samples because they demagnetize better.
Fair enough. Okay. So, yeah, some of that I had up there earlier, but that's helpful. So, yeah, this is the best we have in terms of guesses of what might be happening, and this is a big difference. I don't know whether statistically you would consider that different enough that you can say this, but I like to say that this is different than that. You're not quite smiling and laughing at me, so I guess it's okay.
Well, you have to do the test on a sphere. You can't just
Right.
compare.
Fair enough. Okay. So that brings me to this. How about looking at this a different way? All right. So we've done all that. Now we're going to look at the last part. I actually get to put a little geochemistry in too. All right. Back to this plot. So most of the models depend on these two big chains, Hawaii Emperor and Louisville, and throw in little bits and pieces of these other chains. You just saw me try to tell you that the older ends of these two chains don't seem to agree particularly well in Steinberger's exercises, and well, apparently I didn't do my comparison of paleolatitudes quite right, but I would argue they don't look quite the same. So there's really some arguments to be made that it would be very nice if we had another hotspot to look at, because these things don't seem to be behaving the same way. So we have some stuff over here that seems to be angling the same way as the Emperors and the older part of the Louisville chain. So why don't we take a look over here? Where did this stuff come from? Where does it link to? Right? So is there a young end to that particular chain? This is where you probably figure out that I already know the answer to that. Or at least I'm going to try and convince you I think I know the answer to that. So this stretch here, if you just apply the plate motion models to get an idea of where things come from, basically link this area here to the Cook Austral Islands down here. Here's a more faded plot with literally just coastlines and black lines visible at this point. So these two basically bend right around here, and then they end up right in the Cook Austral Islands, according to the existing plate motion models. Right? So they fit just as well as Hawaii Emperor and Louisville fit, essentially. So that's nice. Can we make this into a longer chain? So this is where Matt's hotspot highway comes in. If you take the 3 different hotspots that sit around in the Cook Austral area, and here's Samoa as well, it becomes really busy here. A lot of hotspots track right through this area here. So Matt had his hotspot highway name for this. And I would argue that as a result of all of them overlapping, you have rush hour right here. It's really busy here with different hotspots. What's that?
The slabs are running back like crazy.
Yeah.
Actually, what occurs to me is maybe not. Maybe the slab does care, because
maybe that's why it tears there.
actually, so why does the Tonga and Kermadec subduction zone end right where the rush hour is, where all those things are crossing? Maybe it's having trouble subducting that thicker crust from these island chains.
Well, it's actually even more complicated. You see this thing here. This is like 2 kilometer thick. It's called Robbie Ridge, and I think the only interpretation I've seen for it is that it's an old part of a ridge, or maybe it's a part of Manihiki when it used to fit somehow into Angtong Java. Whatever it is, it's 2 kilometers thicker. It sits 2 kilometers higher in the ocean than any other ocean basin around it. So there's something in the way here, and this sort of attaches right here into Angtong Java, which is really what sort of holds it down there too. Yeah, so this gets really complicated in terms of having a lot of things pass through there. The fun part is the rush hour part. Can we untangle rush hour? Can we tell which highway or which person's going where on the highway? So Matt made this all in nice little colors. Each plume has a different color, and all the volcanoes are nicely color-coded. Unfortunately, the rocks that they make are not rainbow-colored, so we can't use that. But we can color-code the geochemistry. And so if you look at the geochemistry and you basically map the isotopic compositions into a color coding. Yes.
I see some seismologists shaking their head when they see that tetrahedron.
Yeah, so I know I'm going to talk about making more than just red-eyed and blue-eyed. I'm going to make red-eyed, blue-eyed, gray-eyed, and green-eyed. We'll do this in a second. I first want you to just get the take-home message. Is this area does have all these tracks coming through, but you might notice this is mostly blue running through here, whereas Samoa is red. There's some green that goes through here that ends up going out here somewhere. We can tell these things apart only because the Pacific here, this area here with these hotspots, has pretty much the most extreme isotopic compositions. So they're all on the highway, but isotopically they actually are very different. They have distinct ranges of compositions within each island chain or within each hotspot. But because they're so extreme, you can actually tell them apart.
Jasper, what is white? Is white no data?
We will go through this.
Okay.
So, look at that. Dots. So what I did here is I took the online GeoRock database and basically just color code every hotspot chain by its own color. MATLAB does that randomly for me, so every time I make this, the plot looks different, which is nice. Well, do you really want to spend time designing 30 different colors? So the reason I did this is just to make the point that Bill already tried to make too. All these chains are basically making these little arrays. The way I look at this, it's like a hand with fingers. And each finger is another island chain. Right? And the nice thing about what I'm about to try and convince you of is that it turns out that the hotspots we're working with are the ones that are at the end of some of these fingers. They're far away from the middle. They're not where the main mass of stuff is. All right. Everybody convinced that there's little arrays of dots in the same color? All right, so I did not I was not the first one to hypothesize that, obviously. So this is the glorified picture of what people consider the mantle tetrahedron. So this thing basically encloses all those different dots. And each one of those fields of dots that I had is sort of circumscribed here by what Stan Hart used to refer to as worms. And as you can see, the worms all come together down here in FOSO. You can do exactly the same exercise within the mid-ocean ridges. And if you take the Indian, Atlantic, and Pacific Ocean, they make three trends that basically point in the same direction, and that's where C comes in. So C and FOSO, or Bill made this point before, he called it prima. These things are all roughly in the same place. So something is very common, that's what C stands for, or it's the focal zone. It's the thing that shows up in most of these hotspots in terms of their chemistry, and then they have something else in it that stretches away from the middle. Since both C and FOSO are effectively the way these were defined is, look, this focus is here, and then there was a circle drawn. What I wanted to do was actually define a color scale. So if I want to define a color scale that becomes more and more colorful the further away I get from the middle towards these endpoints, I need to actually have a dot in the middle somehow. And neither FOSO nor C were defined that way. They're both fields. So instead, I went through an exercise of fitting lines through each one of those dots of different data clouds. And what happens when you draw 32 lines? Do they intersect in one point? No, of course not. So instead, what I do is along each one of these trends, you look for the point on that line that minimizes the distance to all 31 other lines. And so you end up with a cluster of little red dots. Each dot is the point on one of these trend lines that is closest to every other line. And so then I just took, since a couple of these are kind of far away, I decided to take the median of this and just sort of describe the uncertainty of that center with just a variation of these dots. And then define from there, from that center point, different colors out in different directions. So I have to mention here, this is done in a different way than originally, but we actually started doing something like this at the first CIDER that I was at. That ended up being an exercise in making pie charts for each one of these hotspots, which then most people didn't like. So this is an improvement on this. But anyway, this ended up coming out of a CIDER exercise. So this is just a way to be able to plot chemistry on a map. And since the geochemistry, as you saw, it's multidimensional, it's hard to put all the isotope numbers and an age and everything else for each sample on a map and then still see any patterns, right? So I have to simplify it. So this is my way of simplifying it, is making a color cube. All right. So going back to the map, here's that little map you saw before. So Gilbert is this guy here, Tokelau is this guy here, and then WPSP is this whole area here. What we have, basically, Cook Australs here, you saw in one of the earlier ones already, is mostly bluite, mostly this high mu component. And Gilbert and Tokelau are also mostly bluite, from gray to blue. So that means in that tetrahedron, what that's showing you is you're going from gray to blue. You're out on this branch here somewhere, right? Once it becomes completely gray, you're in the middle. And then it's anybody's guess. But after that, it fades out to the more saturated colors. So this one has, well, on my screen it looks more blue than it does here. But anyway, this is blue and grayish. This is more bluish. And then there's a few dots here. We'll get to those in a minute. So bluish, both pointing at this area. And then there's ages here. So now you have to start figuring out, okay, how do I tell whether or not these ages are reasonable to correlate them with where the hotspots and the cocostrals are now. So I could try and draw lines here to sort of show where the track would be and what age it would be. That's still not very easy to do. So we'll actually do the opposite. We'll start trying to rotate these things back to where they came from in a minute. Bottom line is I can sort of tell what these things are based on their isotopes, and mapping that into a color code allows me to say, oh yeah, that kind of looks like the stuff that I know is over here.
If you applied this to Hawaii, would it be all the same color?
I actually have the answer here. Hawaii has a little bit of greenish in it, depending on which part of the 1,500 samples people have analyzed for Hawaii you have. Some of the M-member ones are a bit more greenish, and once you get close to the top here, you get closer to a bit more morb-like compositions, and so it turns a little bit darker gray, but it's pretty faded on the screen, so you're not telling a whole lot of it. But yeah, you can tell this is slightly different, this is slightly different. Pitcairn is one of the more green ones as well. This is Society, it's a bit more red, it's a little bit more like Samoa. So you can tell the differences of the different hotspots. But that was my point earlier. These things are very, very, very extreme in terms of where they are in isotope space. Even though the numbers look very similar to you guys probably that don't do the isotope work, they're significantly different enough that we can tell them apart. And if I map it into colors, you can tell that without having to know that that is a big difference. Where was I? All right, going back to this bend here. So I told you earlier that this goes into the plate motion model as a Hawaiian Emperor bend, even though it's not. So this is why it's not. Here is a number of blue dots with ages, and then the bottom end of this chain where it bends, you have gray and green dots that are much older. They're at least 10 million years. This one is like 50 million years older. If you think about the difference here, if you're thinking about, let's be simple and say plate motion is about 100 kilometers per million years. At least 10 million years means you're nearly 1,000, or in this case, 150 years, almost 50 million years, 50 times 100 years, like 5,000 kilometers away. So these things are all pretty close to each other in where they erupt. These guys erupted at least 1,000 kilometers away from where this stuff erupted. In other words, this stuff was already there when this chain crossed it. It's not the same chain. And so making a bend here is not a good idea because this stuff has nothing to do with the blue guys here. We actually proved this a few years ago. We went dredging out here and actually got the seamounts that sit here. They're all blue too. Well, they're in the other plot that I've showed already actually, and I'll show those again in a minute. All right. So I already said it's hard to compare the ages. If I plot ages on the map, I can compare by drawing a predicted plate motion model next to it and try and make you compare it. Or I can just take each volcano and its age and then use a plate motion model to go back to where it came from, right? I can rotate them back to where they originally erupted. So if I do that, you get nice tight little clusters that are all the nice same colors, right? So I can play this game of, are the ages the same, or are the ages in line with what I expect them to be if they were a hotspot or the same hotspot? And I can look at the colors. Are the compositions about the same as what I expect them to be? So you just play this game of rotate them back, plot the colors again for the compositions, and you get nice little clusters of what these hotspots have erupted over time, right? So we can tell these things apart. So Ruru2 is basically neatly running and continuing back into the Gilberts, for instance. All right. For those aficionados that say, well, but you only used one plate motion model at the time we did a bunch of different plate motion models. And the bottom line is that the locations of things may change, but the clusters remain, right? You still have the same kind of clusters of colors. They just shift a little. Particularly when you go to these ones, Raymond is a model that doesn't have the Hawaiian Emperor bend, and it stops at about 60 million years, so things start shifting a fair bit. But you still have clusters of the same sort of thing. All right. So we have the Gilberts, the older part. The Cook Australs are out here. Matt, in his Hotspot Highway paper, pointed out there's a couple of dots in here that look like they should be part of the Cook Australs. Then we went, I sort of referred to this a little earlier, we went dredging out here. There's a few blue dots here already. We now have covered all this with blue dots as well. And so basically we now have bluite coming all the way through here. It bends right here in this area here. So we have another Hawaiian Emperor bend sitting underneath, basically right here where Samoa overlaps a little still. And then we turn north from there. So what that means is effectively we have another chain that makes a Hawaiian Emperor bend and then goes back in time through this chain up north into the sort of western, northwestern Pacific. So another way, that's the reason I put this plot up, another way to look at this is the blue squares were the compositions that were in the Gilberts here. And in this completely washed out plot, it was meant to show you that the blue squares plot really nicely on blue blobs that you can't see. So we're not going to spend time on that. But the bottom line is the blue ones versus the red ones work pretty well because Samoa is very extreme in its compositions and the Cook Australs are pretty darn extreme in their compositions. I can very easily tell these things apart, either by actually looking at the isotopes or I can just color code it so you can see it on a map. All right, so then we have existing data here, existing data here. This is our new data. So we have a nice chain here that goes back into time. And then this is where the next problem is. You can see how the blue dots kind of continue. There's a few pink dots. They're actually kind of different in age. So I suspect this is similar to what we saw here. We don't have a lot of samples here, but volcano-wise, this seemed to continue over here. However, if I draw a predicted plate motion track, it wants to turn a little earlier. There's no volcanoes there, though. So that's an issue. And so that's where we go back to, we can tell back to 80 million years in our plate motion models what to do, more or less. But if we have to go back any further, this is how things were connected. Back in 85, these guys basically said, hey, Easter kind of seems like it goes into the Line Islands, kind of seems like it goes into the Mid-Pacific mountains, this thing here. And this connection has lived on since then with the idea that the Emperor chain, Louisville chain, are equivalent to this area here and this area here. The problem is this stretch here, the Line Islands into the Mid-Pacific. The problem with that is the following. Wait, where did that go? Huh. Oh, it's on the next slide. That's what it is. Okay, never mind. It's on this one. So here's our Line Islands. So there's a problem here. There's two problems, actually. One problem, the age progression. Remember, I told you a couple of million years is okay. There's two plots here. One is argon-argon ages, one is potassium-argon ages. This is the old way people used to do it, but this is pretty sensitive to alteration. If you put a rock on the seafloor for 60 to 80 million years, it's going to be altered. Potassium-argon ages for old rocks from the seafloor is not the best plan. You want argon-argon step heating ages, which is what this is. But look, there's still samples here that are down in the 40s versus samples that are over 80 million years. This is not a few million years. The line islands have tens of millions of years time range, right? That's a problem. This is not a simple hotspot. The other issue, if you look at where this transition was from the mid-Pacific into the line islands, where the line islands started erupting back in time, they were very close to a mid-ocean ridge. So, should we believe that the line islands are truly going to give us a intraplate setting with a plate moving over a plume, or should we be a little worried that there might be some interaction with the ridge system there? You've already seen that the ages don't really work. This is also very worrisome, right? The point I actually didn't make about the argon, Anthony actually has reanalyzed a whole bunch of the line island samples with argon, and they don't look better. So this is not just old data. It really is not age progressive. All right, so what I'm going to argue then is the fact that this doesn't work here, going up here and then, see, it wants to go through all these seamounts here. There's really no chain turning left here. There's a few other chains that are parallel, but there's nothing going left. And so I'm going to argue that the fact that the plate motion model is based on this connection doesn't really force me to believe it, because there's really no reason to believe it. This is probably not a regular hotspot chain, and it was close to a mid-ocean ridge when it was erupted. So instead, I would argue we should be basing our ideas on this thing that actually continues back in time. Anyway, we can step back and just start thinking about what I started off with earlier and promised to talk about, and call it off right after that pretty soon. We can do the same exercise that I did before. We can rotate everything back to where it came from, which is what I've done here now just for the Rurutu and the Samoa area. And so we now have enough dots back in time that are basically continually back in time that there's actually starting to be patterns of how these dots are running. So we are erupting currently over here, but things get older away from the original hotspot. Samoa does something different. This assumes a plate motion model. So am I getting an absolute sense of what these two things are doing? No. But because they're both reconstructed with exactly the same plate motion model, what this tells me is that from about 100 to about 80 million years, the Samoa and the Rurutu hotspot were doing the same thing. Whether they were fixed or moving in the same direction, I don't know, but it's one of those two. After that, they both went off and did something completely different. Samoa going this way, Rurutu going the other way, right? So we can actually step back and think about, we don't necessarily know what the plate motion model should be, but the information that we do get is that we can actually start, if we have enough age dates and we can tell things apart with chemistry, we can start mapping out relative motion, at least, of these things. So I can't, and then I can try and tie this kind of thing back to the real world using paleolatitudes, for instance, to see if what I'm seeing here in shift matches what paleolatitudes would want me to do.
So Jasper, so this suggests that the two hotspots are drifting relative to each other the last 100 million years.
Right.
If you apply a Steinberger approach, I mean, would it describe any of these relative motions that you are suggesting?
Steinberger didn't do Rurutu specifically. He does Samoa. I think the Hart and other people paper from 2004 has it in there. And he basically, so we have a little loop here. He has a loop that goes further left, further west, and then it comes around, and then his model stops. He doesn't really show anything older. But it's similar. And we started looking at some other plots like this as well, where back to about 50 million years, it looks like we're matching Steinberger reasonably well. And after that, his models and our data are starting to go off into space. And then you can go back to the exercise of, is this because the models are breaking up at 50 million years, or are we doing better or worse than them? I don't know. But I think that's where the next step would be to start trying to make those things converge.
So on the last couple slides, I thought what you were kind of indirectly getting at is that for a single long-lived plume...
Where's the mic? Can you please use the mic?
So I thought what you were getting at previously maybe was that for a single long-lived hotspot, its composition didn't change with time. But then I look up here at Samoa
no.
and I see it's got multiple colors.
Yeah, and I do have slides, but I'm going to run out of time pretty soon.
And if it has multiple colors, how does that affect the way you're actually doing these reconstructions based on chemistry?
So it's not that they're unique in only one composition, right? There's a range here. You can tell there's some changing in color. The nice thing is that they're far away. Samoa is a different animal because what it does is, we mentioned this earlier, you build this shield and then you put a little cap on top, a rejuvenated cap on top. In Samoa, that rejuvenated cap actually looks a lot different. Well, thanks for the next slide suggestion. This is where the Samoan shields are, and this is where the rejuvenated stuff is. It shifts. And so it shifts. This is not red and green color-coded like the rest of it, but the green dots that you saw in Samoa are similar to this. They're on this trend towards EM1. That's where the late-stage Samoan rocks sit. And so in the Cook Australs, the array is fairly tight in terms of its range and compositions. In Samoa, it goes out to very extreme EM2, and then the late-stage rocks actually go out towards EM1. Not as extreme in most cases, but it does jump around. So there is an explanation, and it does fit. All right. So in the interest of time, I'll park it here. Just sort of giving you this idea back. I think we have another hotspot chain that we can start using, and I think this exercise of tracing things back to the original locations, we now have enough dots, enough ages, that we can start making something out of the way these things reconstruct back in time to start looking at relative motions. And then trying to tie that to radial latitudes, trying to tie that to the kind of models that Steinberger does. There's more stuff in here about this bend here that we just talked a little bit about. We can start talking about what this should look like once it goes in the trench, things like that, that I had slides for, but I'm going to skip because I want to leave a few minutes at least. So I'll park it right there. Any other questions? Ooh.
So I realize there's a group at UCLA, and this may be sort of controversial, but with the argon-argon dating, there may be some problems using plateau ages. Do you know if those ages were using that method?
Which ages?
So the ages to get
the ones that I used?
Yeah.
They are argon-argon ages, because if you're using potassium argon on altered rocks, you're going to get anything under the sun.
So there's a method called the plateau age, and apparently
Yes.
it can induce essentially a random distribution of ages. An argument that comes out of Mark Harrison's group.
I am not familiar with that one. What I do know is that
yeah, so this may be controversial. I'm just
I don't know.
Yeah.
I mean, what I know is that when you look at things like this, and I don't have the plot with me for this chain, I should have put it in, but when you look at that, if that is a random distribution, it's fairly tight around where the hotspot age progression should be. Usually what Anthony does is on the order of 10 steps or more. That gives you like multiple steps that are all the same, and if he doesn't get enough steps that are the same age, then that's not a good age and it doesn't get used.
So I have a question for your big Western Pacific figure. Can you show this with the hotspot tracks superimposed?
Like the last one you saw? This one?
Yeah. So can you trace out this Rarutu hotspot that you're talking about from beginning to end?
That's the blue one here, right? It starts here and it goes that way, and then this is where I take my artistic freedom and make it go further north.
So you have a Y emperor
prediction
bend.
is.
You have a Y emperor bend.
Yeah, it's right here.
And then you go north, west. Then you have another bend at
about 100 million years.
At 100 million years, then it goes west. So it would go back maybe 120, 130
Yeah, the
million
oldest
years.
one's here about 120.
Okay, so the neat thing here is that you're having a plume that's incredibly long-lived, right? So I want to contrast this with Louise Kellogg's. Louise, are you here? Okay, Louise Kellogg's dynamic convection models. These nice movies that she was showing, where plumes would pulse up and disappear, pulse up and disappear. This is very different. This is a really long-lived, stable feature that is continuous for 120 plus million years, and then maybe longer. It just gets the even older part goes into the trans, the Marianas, right?
So this is the kind of stuff that Torsvik is doing, right? He's arguing that some of the large igneous provinces go up to a few hundred million years and are still effectively sitting. Well, they've moved away, but they would reconstruct pretty much right on top of the edges of these LLSVPs. So if that's true, then these things are sitting in more or less the same place for a substantial amount of time. Ooh, I got some people interested.
Yeah, well, just sort of what, Matt almost said it, but there's a couple of significant things that you haven't really mentioned, and that is that plumes aren't steady, actually. Hawaii is the exception. You look at most plumes, and they're, they tend to be pulsed. And Schilling wrote a paper back in 1975 entitled the Iceland Mantle Blob, because it's discontinuous in time.
Right.
The other thing is
you could even argue that for Hawaii.
What's that?
You could even argue that for Hawaii. It
Exactly.
ramps up to really large islands in the last few million years.
Yeah, and you can see gaps in the chains, and so, they're not really continuous. The other thing is we've known, of course, for a long time that some of us have known that the australs were screwed up and required at least 3 hotspots. You couldn't ever explain them with one hotspot, based both on time and geochemistry.
Right.
And so this kind of fixes that. So, yeah, and we see that, of course, in these not only in the convection models, but in the seismic tomography.
Right.
They seem to be blobs.
There seem to be different things, yeah.
Is there a way to distinguish between like a plume's, advection geochemical signature from whatever the plume might entrain on the way up? Because that should introduce another source of heterogeneity that isn't necessarily unique to that plume.
So what we have is all these chains have this range, right, in isotopic composition, sort of focusing down to the middle, to the FOSO C, whatever you want to call it. So probably you're sampling 2 things. You're sampling some recycled flavor and something common. It's up to you to decide where you would like those to be, right? I don't know what's entraining what. Most people would argue that there's probably plenty of the central stuff, and you're entraining some of the other flavors somewhere. But other than that, it's pretty hard to have any kind of sensitivity to where it was picked up.
Gigi Ferrantonni's argued that the entrained stuff is far enough developed.
Right. Well, yeah.
Whether that's,
Yeah.
That's what she argues.
Nick? I have a really basic question going back to your first slide. So you showed a whole bunch of other linear tracks of things, or not tracks, but linear features in the ocean. How do you know those aren't hotspot tracks? Do they not age progressive? Is it other features? Are there other better explanations? What rules
for
them
some,
out?
yes. So some of these things here have been looked at, and they're not age progressive. Like you go along these chains, and you'll find age ranges over, like, say, 20 million year age range, but any age can pop up anywhere along this thing, right? So that's not age progressive. And to be honest, I suspect that that's what the Line Islands actually are, a similar kind of thing. These are something else. People argue over what they are, whether they're the result of Richter rolls that somehow make some small-scale convection that causes some melting, or if there's some sort of cracking or whatever is going on. So these are examples of what is probably going on somewhere shallow. Some of the dots, I made this map literally by just filtering out, Fourier filtering out the large-scale structure and just making only the little dots. So this has no geology prior knowledge in it, the red dots. It is purely just a spatial filtering. And so it has other things in it, like edges of transform faults and things like that as well. The ocean ridges themselves make seamounts as well that are just purely related to mid-ocean ridge volcanism. So that's in there too.
I think I've heard it repeated. I've heard it repeated over and over that there are fingers that are distinct from each other in geochemical space. But on your second to last slide, with the rejuvenation of the, I guess it was the Samoa hotspot, there is mixing between EM1 and EM2. Or did I misinterpret that? And is that the only place we see sort of webbing between the fingers?
It's webbing, okay. Let's see here.
Yeah, I think if you show that, it really isn't mixing towards the
Okay, so this is what came out of the exercise Matt and I did in a few years ago. This is mixing models like you did the other day. So here the blue guys are the main shield, and then I mix some shield composition with, this is effectively a mixture of upper mantle material, whether it's the asthenosphere, whether it's a plate-like composition, with one of these EM1 compositions. We argued here that this was basically primed by the fact that the last thing this mantle saw before it got to Samoa was the Rarotonga hotspot, which looks like EM1. And so we think a little bit of that was in there, and that mixture that you made there mixes with an EM2 component. So things get complicated. However, this is still a relatively narrow field in that finger diagram. It maybe becomes like your thumb instead of a narrower finger, but it's still pretty narrow. Can you pass it back? Oh, come on.
I sort of have the same question. We've heard now that there's no mixing between these end member components, which would imply that our attempts to do a principal component and independent component analysis was pretty stupid because they're these perfect basis vectors already. I mean, turned around, we kind of did it and it sort of worked, which would sort of imply that there's a number you could give to answer this question. As to, it seems that there's a reduced parameter space that explains yay amount of the data.
Yeah.
And that's possible, right? If there were really, really, really no mixing, it would have been...
Right, so that's what this is, right? This is 3 isotopes that I cut off because it fit better on the page. But neodymium, lead, and strontium, 6,4 lead, neodymium, and strontium isotopes are plotted there because when you take the entire data set, or all hotspots for all the lead isotopes and all the strontium, all the neodymium, you get the majority of the variation in those 3 isotopes. So that's why people like using those 3 isotopes. That's how you can collapse it down to less variables. And then it still spreads out. The Zindler and Hart idea was that if you pick those corners of that tetrahedron, you can make anything else in there by mixing those corners. Which technically is true. On the other hand, since these things look like worms that move to the middle, you would have to mix everything with Fozo, and the other end of each one of these worms would have to be some sort of pre-mixed or pre-made thing before you make the mixture that you see for each one of these island chains. So yeah, I don't know. You could collapse it down to only a couple of end members.
Okay, I know of at least one mineral physicist that really wants coffee right now, so there's probably others. Jasper, thank you very much.